To motivate binary search trees, let's have a look at the data structures that we know and have a look at what they're good at and what they're not so good at. So data structures, we want to be able to do queries and we want to be able to do modifications. So one of the data structures we've seen are max heaps. So max heaps are good for finding the maximum. We can do that in constant time. Max heap are also can also be modified, so we can insert into a max heap in order lock-in time. We actually didn't explicitly discuss deletions in max heaps, and the problem there is if I want to delete in a max heap and I first need to search for the element, there's no efficient way of doing that. After that, we could in principle delete in the same way as we do extract max. So for max heap we saw extract max, which can be done in order lock-in time. So that's a max heap. It's good at finding the maximum, but already if I want to, for instance, find the minimum, there's no efficient way of doing that. The minimum could be at any leaf, so that will take linear time. Let's contrast this to hash tables. So hash tables are good at searching. We can search in constant time. All the modifications, insert and delete, all in constant time, so that's on average and under suitable assumptions. But now a hash table is not so good at anything else, you could say. So for instance, finding the maximum and minimum, there's no efficient way of doing that, so that in principle would take linear time. Actually linear in the size of the data plus the size of the hash table, but let's say that is also order n, then overall maximum and minimum will take order n time in a hash table. Now max heaps are not good for searching, so if I want to search in a max heap, that will take linear time. Also any other operations, so a max heap is really made for finding the maximum, a hash table is really made for searching. So for anything else, probably these data structures will not work that well. So let me contrast this to a very simple data structure, if you would actually want to call it a data structure, and that is a sorted array. So in a sorted array, finding the maximum and minimum is easy because we just have to look at the end and the beginning. Searching, we can do binary search, so that's also very efficient, can be done in order log-n time. Okay, we don't know about other operations right now, but, and now that's a big but for the sorted arrays, we cannot modify them efficiently. So if I want to insert, okay, I can find the correct position using binary search, but then I will have to make space, and making space I have to potentially move a linear number of elements, so that will take linear time. The same holds for deletions. So what we see here, and we've had a few more data structures, so min heaps we could add here, we had the elementary data structures that we discussed. But what we overall see here is that we have data structures that are good at very specific things. Those are also fine in terms of the modifications. But they cannot perform other operations efficiently. So max heap is not good for searching, hash tables are not good for finding the maximum. On the other hand, a sorted array as such is not that bad in terms of queries, but we can't really modify it. So now we would like to have a data structure that is a kind of, you could say, general purpose tool, in the sense that we can do lots of operations or lots of queries efficiently, and in particular we also want to be able to do modifications efficiently. And that's where balanced binary search trees come in. So all of what we've seen in this table, balanced binary search trees will be able to do in order log-n time.